class, we'll get that money into it. Thank you. Thanks, Ray.
Yeah.
Okay. Next section, and before the section starts, I'm going to hand out a little sheet here. If you want to play along and be a forecaster for a day, you can do this individually. You can do it in groups, however you like. Get those all around. So should be enough for everybody if you want to do it individually. So this will come into play a little bit later in this section. You don't have to do anything with it now except kind of have it available. But we're now going to talk a little more in depth about thunderstorms. So the environment, how do they develop, and then we'll look at some tools that you can use to try to both detect where thunderstorms are and forecast where they're going to be in the future. So again, I changed this slide to be our stages of convection. So this is not on the FAA exam, so you can go ahead and, dry thermal stage, we have lift. If you've flown over Arizona to Mexico in the summertime, you can get bumped around pretty good and there's not a cloud in the sky. That's a thermal. Cumulus stage, all going upward, cumulonimbus. And then this last stage, I put in the supercell stage instead of the dissipating. The dissipating is one of the three stages. But this is what can happen basically after the cumulonimbus stage if we have enough of the right ingredients, such as vertical wind shear, and we have that unstable environment, we get this rotating thunderstorm. It gives us our severe thunderstorms. So in the dry thermal stage, again, just pockets of air bubbling up because they've been heated at the ground. Cumulus stage, again, everything is going vertically in the cloud itself. We may have descending air on either side of the cloud, but in the cloud itself we have all rising air. And those motions are generally pretty, I'll call them mild, 500 feet, maybe 1,000 feet per minute vertical motions in that kind of developing cumulus cloud. This is some pictures, some cumulus developing. You can see over the mountain ranges. So why do they develop over mountains? So one of the reasons is because we have sloped surfaces. So when the sun's coming up in the morning, if you have a sloped surface, that surface will heat up faster than a flat surface. So that's why the mountains tend to initiate thunderstorms. You have what we'll call differential heating. It's heating up faster, and the environment can be more unstable over mountains than it can be over flat. We tend to have inversions that occur kind of over the flatter terrain. Those inversions don't occur over the tops of the mountains, so it's a more unstable environment. We call these cumulus, fair weather cumulus basically. And then we get to the cumulonimbus stage, and we have a lot of different vertical motions. Air coming into, feeding the cloud, we have the anvil. The storm motion can be mostly told by the direction of the anvil. So if the anvil's slanted in one direction, that's usually the direction of the upper level winds. That's the direction the storm's likely going to move in. If you have an anvil that just spreads out radially, that means that storm's not moving very fast. It's just kind of hanging out in one spot. And we have now vertical motions, and these can come down again 1,000 to 2,000 feet per minute. In extreme cases, we get into the 5,000 to 6,000 feet per minute vertical motions, both downward as well as upward within these clouds. There's a story about an Air Force pilot. He was in a trainer, I think it was a T-38 back in the late 50s, early 60s, one of the two. Anyway, he had the experience that he flew into a thunderstorm and the plane flamed out. So he had to eject. So he ejects in a thunderstorm, and he was circulated from his count. He passed out at some point, but I think it was 5 loops that he did in the cloud. That he came down, he got sucked back up, went up and came down, and finally came out the other side of the cloud and survived, although he had a concussion and he was ripped to shreds. Hail had beat his arms and all sorts of stuff. So interesting story if you care to look that up.
The counting bit of that said it took him 45 minutes.
Yeah. Yeah, not a fun experience. So in the cumulonimbus stage, we have the fully developed mature thunderstorm, and from looking at cloud, my wife gives me a lot of grief. It's like, oh wow, look at that, and I'll mention some what I see here is a whole bunch of hail in that cloud. So when you see that kind of feathery stuff coming down like that, that's usually a lot of hail that's coming down out of the anvil
Mike,
up there.
doesn't it have a greenish color to it?
So it's different. So yeah, let's talk about that, because a lot of people say, what is that green color? And I've seen this dark green when I've been out storm chasing. When you look at a cloud, we're simply seeing the light that's being reflected to us. So it depends, number one, which side of the cloud you're on, and number two, how much light is actually being absorbed and then reflected and refracted within the cloud itself. So darker clouds, all that means is all the light is being absorbed in a cloud and none is passing through. That's why we see a dark cloud, especially if you're on the, sun's on the other side. It's not at your back, it's on the other side. So we'll see a dark cloud. Now, a lot of times that cloud becomes green when you're looking at it. And the reason of that cloud contains a lot of ice crystals, primarily hail. So a cloud that turns green, the hail actually changes the diffusion refractivity of the light itself as it's going through the cloud, and it gives it that greenish color. So that's all that greenish is an indication of there's a lot of hail in that actual cloud. So we get to the supercell stage, and again, we have this rotating kind of cloud. You have the mammatus clouds that can hang out along the bases. We have the rear flanking downdraft, all sorts of different stuff. Still a lot of inflow coming out. We got outflow in different directions. A lot of things going on. And a great picture taken by National Weather Service when they're out in their vortex project. So you can see here, tornado on the ground. We have the wall cloud, and then this overshooting. So here's the anvil, and then this top is probably going up about 5,000 feet into the stratosphere. So the anvil forms at the tropopause, and typically the tropopause is really stable, steep inversion. Most clouds flatten out. Well, when you have so much energy going up, it can actually shoot through the tropopause, and that's what we call an overshooting top. And overshooting tops are theoretically linked to tornadoes on the ground. We don't know the exact kind of mechanism that goes on when you have this overshooting top and then the collapse of that, and then tornadoes tend to come out of the things on the bottom. But good spot to be in for watching such an event.
Tornadoes typically at the back end?
Yeah, so good question. So when you're out storm chasing, this cloud is likely going in this direction. The tornado's on the back side, typically the back kind of front side of that storm.
And Mike, are these usually associated with frontal? Are these frontal storms, or can they be both?
So these are mostly, of the frontal or convergence type of thunderstorms.
Because of the wind?
Because of the shear that you need to get the rotation, yeah. But the other interesting thing that I've experienced when I've been out storm chasing, when you have a line of thunderstorms, you tend not to get a lot of tornadoes. When you have isolated discrete cells, those are the ones that produce a lot of the tornadoes. The lines of thunderstorms give you a lot of outflow and winds, 80 to 100 mile winds out in front of them from the outflow. Very strong damaging winds, but usually not the rotation. So again, the other thing as pilots we want to be concerned about are these things like outflows and gust fronts. So as the air and precipitation comes down out of the cloud, we call that a downburst or a microburst, the air spreads out radially, and as it does, we still have inflow supporting the cloud, and that boundary we call the gust front. So we have outflow and then inflow, very sharp wind difference across that gust front. And if you're in the terminal environment, you have thunderstorms like a DIA, for example, or even here at Centennial, you have to be aware of where these gust fronts are, because they can be very tricky to fly through at low levels. This is kind of what it looks like in a real picture. You can see here the precip and coming down, and you can see the air flowing out over the water. As it hits, it spreads out.
And you said you have to be aware. How do you make yourself aware?
Yeah, it's a good question. So hopefully the tower has some indication of this event going on. So they've installed both the terminal Doppler weather radar systems out of DIA, and they also have installed a lot of localized wind sensors in the terminal environment that should give the tower an indication that a microburst and an associated gust front is in the vicinity, and they should alert pilots of that. Unfortunately, it doesn't always happen, especially at smaller airports, you're not going to get those kind of indications. But at some of the larger airports, hopefully they have systems, the tower personnel are monitoring and can tell you that there's a gust front or a microburst alert, and they'll usually tell you plus 20, plus 30, etc., not that you're going to have across that gust front.
Mike, can a gust front span a large horizontal distance?
Yes. So they can go out, I've seen them out 70 miles from a large developed either line of thunderstorms or a central thunderstorm. You can see the wind direction change out 50 to 70 miles sometimes.
What can you expect on your previous slide there? What can you expect on the outside of the cloud flying? You're flying around the cloud.
Yes, you're saying you're flying up here.
Or, yeah, up where your arrow is or somewhere.
Yeah.
What do you expect outside that?
Yeah, so outside, again, it depends what stage the cloud is in. So let's call this a mature thunderstorm. We have both so a lot of the motions are going to be vertically going up in here, and then they're going to be coming down in here. Out here, typically you're not going to have the strong vertical motions. You're going to have some motions, but not nearly as strong. So typically the general rule of thumb is to say 25 miles away from the cloud itself. If you do that, generally, you're not going to have any of those strong motions or turbulence.
Up in the mountains, several times I've come around where they look like a very symmetrical mushroom. They're not shaped like that. There's probably more orographic, I would think. But they're very slow movers too. And I've often wondered just what's going on around that cloud because it's so symmetrical.
Yeah, typically not a whole lot. Generally, if you fly on the outsides of these,
It's through there.
yeah, you're typically not going to get a lot of bumps. It's really the key is to stay out of the cloud itself, where all the motions are.
Hail can also be thrown out of the top of it.
Yeah.
It can. So that's the one thing to note. If you have an anvil especially, hail can get pumped up into the anvil and then fall out in clear air. And that's why the rule of staying 25 miles away from the core of the storm, because that hail can come out in clear air underneath an anvil, for example. Good point.
You know, that last illustration, the one before, explains why at an ATC briefing at the controllers, they were saying that DIA is notorious for the microbursts. And so much so that an aircraft can be landing into a headwind and halfway down the runway it turns into a tailwind.
Oh yeah.
And that explains it right there.
Yeah, you can absolutely, think of a runway being 2 miles long. You can absolutely have a gust front right in the middle of that runway. Not such a good scenario for takeoff and landing. And then, what we talk about is when we're flying through these kind of microbursts, if you will, an aircraft coming into it, all of a sudden you got a headwind. It's like, hey, everything's pretty good here. Now all of a sudden we got air coming down, and this air can be coming down 500 feet per minute all the way up to, let's say, 5,000 feet per minute, and all of a sudden you're going to lose lift. And now you're trying to exit, and you have a tailwind. So very hard to get performance when you have a tailwind, and this is where a lot of the early kind of incidents occurred in aviation. So this is a case, Pan Am 759. This is back at New Orleans. In the early days, this is 1982, I believe, July of 82. This was a 727 taken off to the east at New Orleans. And this thunderstorm was sitting right off the end of the runway. And in those days, the controller was like, hey, if you want to take off, go for it,
Yeah.
So he rolls, he takes off, everything's good, and then he flies through the microburst. All of a sudden, you start getting decreased lift, air's pushing you down. And by the way, this was Ted Fujita who actually did this analysis. And then started losing lift, and again, now he's in the tailwind section, couldn't get lift, tried to put on full power, tilt, and he hit some trees, and then eventually came down off the end of the runway out in Kenner. And this was the result of where they came down in that crash. So again, the early days of kind of understanding what microbursts can do in a terminal environment. Another crash, a few years later, this is 1985 in August, and this was Dallas-Fort Worth. So this was an L-1011, Delta 191, was coming in from Fort Lauderdale, stopping in Dallas, and heading on to Los Angeles. And it was a typical summer day in Texas, everything was looking pretty good, and all of a sudden a thunderstorm popped up just to the north of the field. And it developed very quickly. So, if you read the transcripts of this, the captain and the FO were sitting there looking, going, hey, I see something ahead, and all of a sudden the FO says, hey, I saw lightning in this cloud. Lightning's an indication you're probably having something develop fairly quickly. And a microburst, fairly strong microburst, occurred. And you can see the track. This is the track of the aircraft coming in, going right through that microburst as he was at pretty low levels, below 1,000 feet, trying to get to the runway itself, and ended up coming up short of the runway because of that microburst. Again, couldn't climb out of it and came down on the ground there, but fairly close to the runway. It came across one of the highways there at DFW, fairly close to the runway. So again, the thunderstorm environment, lift, what do we want? We want a front convergence line, something to give it lift, or a sunny day in which the maximum temperature exceeds what we call the convective temperature. That means that you have temperature high enough that you're getting enough lift to produce a thunderstorm from the temperature, the heating itself. Moisture. We want dew points at least 40 degrees higher here in Colorado. So this is a Colorado kind of perspective. The higher the dew points we have, 50 to even 60. We get into our North American monsoon season, we can have 60-degree dew points here in eastern Colorado. So the higher dew points, the better it is for thunderstorms. And precipitable water is kind of the amount of water in the column of atmosphere. We want those to be about 3/4 of an inch here in Colorado. We'll look at some soundings to tell you what that really means. And from the stability standpoint, we want our lapse rates to be in the 2 to 3 degrees C per 1,000 feet, close to that dry adiabatic lapse rate. We want a lifted index lower than +2, a K index of 25 or more, and 500 K. And there's a handout in the back there that has some of these indexes, Colorado kind of specific indexes on it, that you can take a look at. So for severe thunderstorms, again, we need the lift, we want moisture, more moisture, higher dew points, we want less stability, so more instability. So our lifted index of -2, K index of 35, capes of 1,000, and no cap. And that will get us to our severe thunderstorm environment here in Colorado. Which, here in Colorado, severe thunderstorm season really kicks off in about June. June is our kind of primary month. It goes into July as well. So what is the lifted index? We've talked about what we want. So the lifted index, I'm not going to try to explain how you get to it on a SQT and all that stuff. It's basically if you lift a parcel of air adiabatically, is that parcel going to be warmer or colder than the surrounding air when it gets to 500 millibars? That's by definition what our lifted index. The number itself is just the degrees Celsius, either warmer or colder. That's real basic on what the lifted index is. So if it's 0, it means it's at the same temperature. So that would infer that we have some instability. If it's positive, it means that the air is actually colder than the surrounding air, and it's not going to continue to rise. The lower the lifted index, the more instability we have. So the more negative the number is, the more instability, the greater chance of thunderstorms, and the greater chance of severe thunderstorms, the lower that number gets. K index is a little bit different. It takes moisture into account at 850 and 500 millibars as well as 700 millibars. And it is the opposite of the lifted index. So the higher the K number, the greater your chance of thunderstorms. The lower the number, the less of a chance. So we use it in probabilistic terms here. You see here, if your K is greater than 40, hey, really good chance of thunderstorms. If it's less than 15, less than a 10% chance. And again, those numbers are on that handout like that. So CAPE, convective available potential energy. It's kind of become the de facto standard for instability in thunderstorms in the last, let's say, 5 to 10 years. And it uses a SQT log P diagram, and it calculates the positive and negative area in a sounding. So as your temperature is going up, any area where it's positive means that that parcel that's been lifted is warmer than the surrounding air. If it's negative area, that means that that parcel is colder at that point. So you count up all the positive and negative areas, and that's how you get to the number of CAPE. So our CAPE values, again, if it's less than 500, your potential for convection is pretty low. We get above 500. Here in Colorado, we can get some pretty good convection if we have cakes over 500 to 1,000. If we're in 1,000, 1 to 2,000, we're in the severe weather, severe thunderstorm risk here in Colorado. And over 2,000, you got a pretty good chance of tornadoes here in Colorado. So our thunderstorm glossary includes this dry line, which we talked about earlier. It's depicted this way on a map. West Texas is kind of the key area for dry lines. And again, you look at the dew points on the east side of this dry line. You got dew points 16 Celsius, you're around 60 degree Fahrenheit, pretty good dew points. The west side of this line, you got -4, -6. You're below 30 degrees Fahrenheit. So a big difference in moisture across that dry line. That's why they call it a dry line. Real moist out here, dry, and it just initiates thunderstorms will develop along that line, and then they move away from that line into the moist area.
Mike,
Yeah.
the difference in that symbol between the dry line and the ridge.
So this one back here is a trough.
No, the dry line, it looks like a ridge.
Oh, no, that's just, it's an open warm front, if you will, the barbs on it. That's whatever, for whatever reason, how they decided to depict a dry line. These are actually warm front pips, if you will, but they're not filled in, is how we define a dry line. If they were filled in, that would be a warm front. Okay, level of free convection. So that's basically the level at which a parcel of air that's been lifted will continue to rise. So that's important when we look at stability of the atmosphere. If that lifted parcel makes it to the level of free convection, it will continue to rise until we hit the equilibrium level. So that's which parcel now becomes colder. If it's already been lifted through this LFC, typically the equilibrium level will be the tropopause. It'll keep going until it hits the tropopause. So now we're going to look at some tools to look at upper level and surface maps, dew point. How do you determine if thunderstorms are going to develop, and if they do, where are they going to be in the future? So we're going to use all these tools here to look at all this information to determine, hey, are thunderstorms going to develop, and if so, where are they going to be in the future? This handout's going to come into play here because you get to play forecaster for a little bit here. So I picked a day with we'll call it a low to moderate thunderstorm potential. It happened to be March 6, 2018. I was headed out to the Women in Aviation conference to talk to them about thunderstorms. And so I looked at this day to look at what was the thunderstorm potential. So you have a blank map in your hand, and eventually you're going to select which states you believe will have thunderstorms in them at 0Z on this day. So we're going to look at data in the morning, we're going to look at some forecast stuff, and then you're going to get to pick where you think thunderstorms are going to exist. So here's our 300 millibar, 30,000 feet in the atmosphere. Notice big upper level low right here over the kind of Midwest part of the country. Ridge along the west coast, ridge along the east coast. Okay, upper level ridge. This is how we define it, kind of that bulge of heights. Yellow lines are the height of the 300 millibar surface, and that bulge along the west coast. And in the middle, we have this trough. Did our projection come loose? That's not good.
There you
Okay, let's try that. Either that or my clicker's going out. So 500 millibars, again, we have a low in that similar position. We have the 300 millibar, and which is we call this a closed low, a loft. So a lot of times we talk about upper level troughs. When we have a closed circulation, we call that a closed upper low. That's a more intense form of an upper level trough. When we have that closed circulation, like we do today to the south of us, over southeast Colorado.
Is that another law up in Canada about it?
Yes, that is indeed. They're all kind of part of that same thing here. And then the ridge, east coast, ridge on the west coast. So if I were to look at this pattern in general, I would say, hey, pretty good weather, east coast, pretty good weather, west coast, maybe not so good central part of the country. In general speak. 700 millibars, that low becomes even more intense. So this is a pretty strong closed low circulation. You can see pretty strong winds here on the back side of that upper low. And finally we get to the surface, and sure enough, hey, it's March, we got enough cold air, we got a pretty good snowstorm going on in the Midwest here with that circulation. And we got a frontal system, and we got some pretty good convection down here along the Gulf Coast because of that front. Front's causing the lift, we have enough instability, moisture, etc., and we got some pretty good precipitation down this region. As expected, hey, pretty good weather on the West Coast, pretty decent here along the East Coast because of those upper level ranges. So infrared satellite, again, you can see that circulation over Iowa there in the snow, and again, that pretty good convection down through the Gulf Coast. So this is our dew point analysis. Again, same time, 12Z. And we notice here, anything in blue, I think, is around 56 degrees or higher in the light blue. So those are our areas, above 50 is what we're kind of looking for thunderstorm potential. That 50-degree air, extends up in here where we saw that convection going on. So this is our CAPE in SIN. So I didn't talk about SIN. Convective inhibition goes along with CAPE. So in that diagram I showed you, we had positive areas, that's CAPE. The negative areas are SIN, convective inhibition. And again, those two kind of weigh each other out. If the CAPE exceeds the positive, exceeds the negative, we have a positive CAPE. If the SIN exceeds the CAPE, then we have negative values. Not much thunderstorm. So the red lines here are your isoplus of CAPE. So you have 1,000 in this one and 500 here is our CAPE values. These are out over the Gulf of Mexico. The shaded areas are convective inhibition. So those are areas in which you would not expect instability. It's in that positive kind of red area you would expect the convection. And here's our 12Z. Our thunderstorms are all occurring here along Texas, Louisiana, Gulf Coast. Along with that front low here, front comes down through here. And this was visible, satellite infrared. We even got some thunderstorms now occurring up here outside of Atlanta, again along that frontal boundary. So this is our water vapor image, just another form of satellite that looks at water vapor instead of clouds. So we have more moisture in these white areas, lots of water vapor, drier where you have blues and yellows. And again, our reflectivity and our tops. So you notice here some of our tops are in this kind of dark blue range up around 30,000 feet. So for March, that's not too bad. So convective segments were in effect at this time at 15Z for those areas of active convection. And we're going to look at some soundings now. So how many people have never seen one of these diagrams before? Okay, so this is a diagram that's derived from a radiosonde balloon. So around the world, we set off weather balloons twice a day, 0Z and 12Z. About 80 of them go off throughout the United States, mostly where there's a weather forecast office. And what the weather balloon does, it senses the atmosphere, and it sends that information back down to the ground. When we get that info, we can plot it on a diagram that we call a skew-T log P diagram. And the reason we call it that is that the temperature, these blue lines, every 10 degrees Celsius are skewed, so skew-T. And pressure, the horizontal lines going across are pressure. So 700 millibars, 600, 500, 400, 300, etc. So logarithmic pressure, skewed temperature, skew-T log P. The trace of temperature in the atmosphere is this red line right there. So that's what the temperature is actually doing as the balloon goes up. The line green is the trace of dew point. So where temperature and dew point are close together, we would expect clouds. Where they're farther apart, we would expect dry air. So this happens to be at Reno at 1200Z on this day. So it's the morning sounding. And we have a bunch of numbers at the top here. So our temperature at takeoff was 29 Fahrenheit. Our dew point was 21. Our lifted index is 17.9. Remember, we wanted lifted index to be negative for the atmosphere to be unstable. 17.9 tells us this atmosphere is pretty darn stable. We also have the K-index, -10. Remember, we wanted K-index to be high for thunderstorms. This is negative, not a good thunderstorm. And our precipitable water, 0.36 centimeters. What that means is that if I were to take a cylinder 1 centimeter in diameter, and I were to put it all the way from the bottom to the top of the atmosphere, and I were to capture the air in there and I were to cap it off, and then I condensed all that water vapor into liquid, how much liquid would I have at the bottom of my column? And in this case, I would have 1/3 of a centimeter. That's not a lot of water out of the column of the atmosphere. Okay, so that's a pretty dry indication of a dry atmosphere. Reno, it's a pretty dry place, so we would expect to kind of see that. The last thing are the winds. As the balloon goes up, it's getting wind direction, wind speed, and it's plotting those. Winds like this are from the west, north, east, south. So these winds are westerly. Down here at the bottom, we have southerly winds. That's how you look at the bars.
Which one's the dry adiabat?
Oh, good point. So, dashed red lines are our dry adiabats. So if we were to lift air, that's how that parcel would be lifted. We also have things called moist adiabats. Those are these dashed green lines right here. So that's our moist adiabatic collapse rate, which is 2 degrees C per thousand instead of 3 degrees C per thousand. Then we have our mixing ratio lines, these yellow ones. You don't need to worry about those. They're for other things. The other thing the diagram tells us, pretty important, LCL, lifted condensation level. That's telling us if the air is lifted mechanically, so like by a mountain or something like that, this is the altitude that the base of that cloud would be. So for pilots, useful information. The CCL, convective condensation level, is the base of a cloud that's formed by heating, lift by heating. Okay, so they're usually different. The CCL is always at or higher than the LCL. Okay, not much going on in Reno. Omaha, getting into the central part of the country where we had kind of closer to that upper level trough, and you notice here, temperature and dew point really close together for a large part of the atmosphere. What does that mean? Yeah, we got solid clouds over Omaha going up. If you were to climb through this, you'd be in clouds most of the way. This point right here, where the temperature starts increasing or going up, that's the tropopause. So here at Omaha, our tropopause is down around 25,000 feet because of that upper low. When you have an upper level low like that, the tropopause is going to be much lower. So pretty low. And our LCL and CCL pretty close together. And where's our 0 degrees Celsius line? Here. All these clouds are below freezing. So what would you expect? Ice. Yeah. Yeah, good profile for a whole lot of icing going on there. So these diagrams can tell you a fair amount of information about the local environment. So we here in Denver have a sounding in Denver, so pretty handy.
Also have very high winds at low levels.
Yeah, good catch. Look at these 50, 60 knot winds at low levels. So you're on the back side of that upper low. Yeah, probably not a good day to fly. We'll get in the car that day. So Atlanta, Georgia. Again, temperature and dew point on top of each other as we go up here. So again, clouds, where's our 0 degrees Celsius? Right there around 700 millibars, which is about 10,000 feet. So above 10,000, you would expect some icing. Below that, just simply precipitation. And again, our lifted index, 2.6. So we're getting lower, closer to 0. And our K index is 34. So it's getting up in that fairly high range. And we noticed there was a thunderstorm pretty close to Atlanta right at this time. So Jacksonville. Yeah, not a whole lot of moisture. It's kind of shaky on there. The winds, and look at our precipitable water of 1.77. Not real impressive for Florida, but still a lot more than Reno. But our lifted index is 12. K is 6, so not all that unstable.
Hey, Mike,
Yeah.
would it be fair to deduce that you might get a lot of layered clouds in a case like this as opposed
Yeah.
to the previous?
Yes. So the previous one, it was solid. This one, you
solid.
may have some layers where they get close. Absolutely. Yep. But not real thick layers, as you can see. Yeah. Okay, so we've seen kind of the current picture in the morning. your job as a forecaster is now to determine where a thunderstorm is going to be at 0Z. We looked at 12Z. 12 hours later, where a thunderstorm is going to be occurring. So we'll look at some tools to try to help us understand where that's going to be. So this is our convective outlook. Tells us for the next 24 hours where general thunderstorms are possible, the light shaded green areas, and along the Florida coast, they're saying there's a marginal risk of severe thunderstorms. That's what that darker green indicates there.
In the arrows, that means the area in question is to the right? of that
Correct.
line?
Yeah, think of your hand and your thumb. So your hand's going in the direction of the arrow, your thumb is pointing to the area that's inside that. You know, those are the things we learned in weather school.
If you're left-handed, you
So 2% chance, less than 2, pretty low chance of tornadoes, but you know they put the marginal risk in there anyway. So here's our Cape and SIN forecast at 0Z. So this is telling us now, if we look at our diagram, anything greater than in the gray area, so anything in this blue is above 1,000, 500 is the dark gray. So that's where Capes greater than 500 and 1,000 are expected to be at 0Z that afternoon. This is our extended convective forecast plot. I was having a discussion with someone earlier. So this is put out primarily for the use of air traffic managers. So this is put out between the National Weather Service, some airline meteorology groups, and the FAA to really determine where thunderstorms may impact flow, air traffic flow across the United States. So what they're telling us here is that at 0Z, we're in this 60 to 79% chance. This is 40 to 59% chance. So we have this area 60, this area lower. This is where thunderstorms are expected at 0Z from a flow management perspective. Now we have our NAM reflectivity forecast. This is a numerical model, North American model. And it's telling us, again, this is reflectivity, so it looks like radar, what we would normally see on an X-rad plot. And it's telling us where that rain is going to be at 0Z that afternoon. So this cannot tell you precisely where thunderstorms are going to be. It's just telling you the rate of precipitation. Generally, the higher the rate of precip, we think the better the chance there's a thunderstorm involved. But it's not 100% correlation. A different model, the HER, High Resolution Rapid Refresh, the same look at 0Z. Different model, you get a slightly different forecast. But you're showing the same thing, you're showing reflectivity. Okay, this is just again another forecast of where reflectivity is going to be at 0Z. This is the Maple product. And now, if we did our AWC flight path tool, and we did a flight from Reno down to Orlando, this is what our relative humidity looks like at 40,000 feet. We're in a Learjet for this flight. They fly nicer aircraft. If we look at the cross section, we get up at 40, but if we look down here, what we're actually looking at in this profile is a front. Okay, where this moisture comes down to the ground and extends up in the atmosphere is actually a front. So if we're going to descend through this, we're actually coming down through that front. That's what it looks like in this diagram. Temperature profile, pretty warm temps over Orlando, freezing levels up here around 12,000. So, all the data you've seen now, you get to be a forecaster. On the map you have, place an X in each state that you think there will be a thunderstorm right at 0Z. You get 5 correct points for each state that you get correct. And if you put an X in a state that doesn't have a thunderstorm, you get 1 point deducted. So you can't just put an X in every state. That's kind of the deal here. So take a minute or two. Think of this in the context of, again, you're in that aircraft that's planning that flight. So where do you think thunderstorms are going to be that may impact your route?
Reno to where?
Well, this is just any state in the country. But as a pilot, that's how I would think about it is, hey, I got a flight. What areas am I going to have to worry about thunderstorms? So I'm plotting out mentally in my mind what states may have activity that I have to be worried about. Now, I will say, unfortunately, the women in aviation got prizes for who got this correct. They were nice little battery packs. I couldn't get marketing to give me any of those. Okay, everybody kind of got an idea? All right. And this is going to tell you what a mean instructor I am. So here's our reflectivity at 0Z. So close to what the models were kind of suggesting. You know, it looks similar to what the NAM and the HER model were suggesting. And where are thunderstorms? Gulf of Mexico, not one to be found in the United States. So the key thing that I took away from this was that Cape forecast. If you looked at that Cape forecast, it was indeed, you know, that 500 line only went about up into here, and that's indeed where the thunderstorms exist. So if you got a 0, you were spot on. Anybody get 0? Yeah, that's what the map should look like. But yet, an hour later, look at it, we had some of these thunderstorms pop up here in West Virginia. So it just goes to show you, you know, an exact spot in time. When I was in school, you got graded on forecasting at exact time. As a pilot, you're looking at the broader picture. So yeah, you want to look at where everything's going on. You know, and really the deal here is it depends on where your personal minimums are. You know, do I need to avoid all thunderstorms and I can't fly? Can I safely navigate some? Do I monitor? Do I look at a minimum DBZ that I want? Depending on your experience, what aircraft you're in, who your passengers are potentially, really plays into all these decisions that you make when you're planning a flight and what you're trying to avoid. So we'll look at more detail in our next segment coming up where we actually do an actual flight scenario in a little more detail than this. Yeah, I don't know if we want to do this or not. This is just it's a 2-minute video of maybe I'll put it on at the break here. It's just a rotating kind of mesocycle and kind of cool, but I'll play that during the break. And again, yeah, just more cool stuff you can see. Okay, so in our theme that we were on last time, which state has the highest number of tornado fatalities in 2017? I'm not trying to scare you moving to Texas or anything, but in this case, pick the state or the letter that you think had the highest number of fatalities in 2017. And same drill, put them up on the computer, let's take about a 10-minute break.